welcome. Thank you for joining us. You are in the right place if you're looking for the data science webinar. I can see we've got quite a few people joining now. Just whilst we're waiting for people to join, if you want to pop your name and where you're from in the chat, it's useful sometimes. I think we'll have some questions later on as well. So if people want to refer to each other or know where we're coming from with different types of questions, I think we've got a pretty broad panel today. Good afternoon, everybody. Still coming in thick and fast. Here we go. Good afternoon, everybody who's just joining us. Just to let you know, we are recording today's session. We've already kicked that off, just so everybody's aware. If you want to, whilst we're waiting for everybody else to join, type into the chat where you're from or why you're joining us today or any particular questions you'd like to touch on. There will be an opportunity for some questions at the end, I think, but we'll make the most of the time that we've got whilst we're waiting for everybody. You are in the right place if you're looking for the data science webinar. I hope everybody's having a good day so far. We'll kick off in a minute or two. We were expecting quite a few people today.
I think we'll go for it, Jack.
I think so. Normally what happens is I say everything is slowed down. We don't seem to have anybody else joining us. And that seems to be the point at which we get our last flurry. Here we go. There we go. I will admit these people and then say for the last time, hello, Brunhoundau. Good afternoon, everybody. Thank you for joining us today. We are starting our series of webinars that we're hosting our friends at the data science unit in Welsh Government. We had a bit of an introductory call at the start of summer. We took a break for summer and now we're very much back to school and we're all going to be learning more about data science and specifically ancient woodlands, I think it is today. Yeah, lost woodlands and looking at the data sets around ancient woodlands in Wales. So I think without further ado, I will introduce us. 1 second. Seems to have minimized my screen. I will introduce our counterparts at the data science unit in Welsh Government. For those of us who joined ahead of the summer break, they'll know that we're going to do a series of webinars in the near future. They've done some amazing work internally and they want to share it as much as possible with the rest of Wales and help everybody else learn from their experiences. I think we teased this in the overview session that we had previously. So we're looking forward to getting into the details now of what Evie's done and what insight that we found and the process around it. So without further ado, I'm going to pass over to Evie Brown from the data science unit. And thank you very much.
Brilliant, thank you. I'll just take control. So thanks for joining, everyone. Today, I'm going to be presenting some work that the data science unit has been working on, which is looking at using computer vision models to create a lost data set, a lost woodland data set for Wales. So we've got a few slides to get through, so I'll make a start. So in this session, first of all, I'm going to go over a bit of an introduction to the project, so why it was useful, what the problem was, that sort of thing. I'll then talk a bit more about the data and the type of model that we used. We'll then share our first outputs, so our first kind of predictions from our model to identify lost woodlands in Wales. And then talk a bit about the next steps, so what we've been doing since to identify different types of trees on these maps as well. But before going into sort of the technical detail, I guess it's good to get some context behind the project. So in sort of February, March time, CADU approached the data science unit in Welsh Government with a problem to do with being able to identify areas of ancient woodland in Wales. So CADU are the Welsh Government's Historic Environment Service, and they're interested in areas of lost woodland. So these are areas that contained woodland in the past, but no longer contain woodland currently, because there's great potential for these areas to support tree growth. So if you were going to replant areas of woodland, you'd want to target these areas because having supported trees in the past, there might be a good root network there, or the soil might be suitable, for example. So this would really help kind of replantation efforts to target areas where we want to plant more trees, which will help us meet targets like the National Forest for Wales, and also help eliminate woodland proposal schemes that might be inappropriate just because the land or the terrain isn't suitable for that sort of tree growth. So this is why this information or this data is useful, but at the moment we don't have a consistent data set containing these areas in Wales. And if we were going to do this manually, i.e. going through all of the historic maps and labelling the areas of woodland ourselves, it would take a long time and it would be not very consistent, which is kind of where the data science unit came in to offer some support to use a AI model instead to do this automatically. So just kind of like a bit of an illustration, I guess, of what we're actually looking for. So the image at the top here shows an area of Montgomeryshire, and you can quite see clearly on the left that we've got two areas of woodland. So on the left, we've got the historic maps, so we can see symbols of trees, for example, and then on the right, we've got modern satellite imagery, and we can see that these woodland still exist. We've still got two quite clear areas, and the geographies are very similar as well. If we then look at the image on the bottom, we can see again another area of Montgomeryshire, and again historically we can see that woodland existed in these areas. However, if we look on the satellite image at the right, woodland no longer exists here. So this would be a good place to target sort of woodland replantation or creation, because we can quite clearly see there's an opportunity there where woodland existed in the past but no longer exists now. And these two areas are less than half a mile from each other. So it would really help kind of target exact, precise locations where we can focus our replantation efforts. So that's sort of like our kind of premise, if you like. And then we broke the project into 4 key areas or 4 key requirements. First of all, we needed to make sure that we had the data available that was suitable, had the right granularity so we could actually identify different terrains. And it needed to be geo-referenced, so we'd be able to use it in geospatial software and it would be useful for CADU. By doing this, we needed the right infrastructure, both the geospatial infrastructure like QGIS, but also infrastructure that we could use to host our computer vision model, and that was also scalable, so we could use it to predict on across the whole of Wales, which was our sort of long-term aim. We then needed a model that could be run on this infrastructure that was open sourced, and that was efficient and easy to use. But most importantly, we needed it to be accurate so that it would be predicting the right areas of ancient woodland. And then finally, we needed outputs that we could share that would be understandable and easy to use, and most importantly, easy for us to specify the caveats or the risks involved in maybe using this specifically. So moving on first to the overview of the data set. So we used Ordnance Survey landmark maps, which are actually hosted by the National Library of Scotland and available to Welsh Government through our OS public sector licence. So these historic counties are made up of 13 different files, which are called GeoTIFF files, and we used the first version of these, so the earliest ones available, which map from sort of the 1840s. The 25-inch scale meant that we had sufficient symbols, like the detail was good enough for us to be able to identify buildings, parkland, farms, and most importantly, woodland. And then we could use these in like QGIS and other geospatial software because they were georeferenced. So these are all the good points, I guess, of using this data. The not so good points was that these files are very big. It's very difficult to use them in computer vision models, so we needed to convert them into a smaller file type like PNGs that we could use to actually predict on. And this is an example of an area of our landmark tile. So this is an area of Anglesey, and we can see that there are different types of symbols that represent different types of areas of woodland. We've got woodland that's contained in boundaries. We've got woodland that's more sparsely distributed over a large area. We've also got different symbols that represent different types of trees. And in all cases, we've actually got other symbols like map references or names of places, which are within the area of woodland as well, that we need to take into account when training our model. So what we did first is pre-process our data. So essentially we needed to convert it into a file which we could use in our computer vision model. So we took each GeoTIFF file, each of our 13 counties, and split them up into grids of 200 meters by 200 meters. So step 1 shows the original part of an original GeoTIFF file, and step 2 shows how this is then cut into smaller PNGs. So once we apply this across the whole of Wales, then we get nearly 600,000 images. Now that's a lot of images to process, and like one of the aims of this project was to try and to make it as efficient as possible. So our next step was to retarget the areas of the maps where we think that woodland is most likely to exist. And one area where we're pretty confident that there will be no woodland that exists is areas of coastline or the sea, because there's a lot of white space, and equally a lot of the GeoTIFF files are actually made up of basically blank tiles. So the next step we did is basically review all of our individual tiles. We calculated the percentage of black and white pixels and removed any tiles where there was less than 99, or they removed any tiles where we had greater than 99% coverage of a black or white pixel. So what this actually meant, if you look at the images here, the images in grey are tiles that are removed, and then the images of the actual map have been retained. And we can see that like a lot of our coastal areas or a lot of areas where we might have a single word have been removed at this step. So it just cuts down the number of initial images that we need to predict on. And then if we apply this across the whole of Anglesey, we can kind of use this as a bit of a QA exercise. Again, the grey squares have been ones that have been removed, and then the red squares are the ones that have been retained. And if we look closely, we can see that as well as like the sea or the area around a county, what we've also removed is areas of blank space within counties as well. So this is where the terrain might be very open landscape, might be very barren. It doesn't contain any kind of many symbols, for example, and therefore it won't contain woodland, and we can remove it at this stage rather than asking the model to identify or to predict on every single image on the map across Wales. So that's our data. We've now slimmed it down to a targeted series of images that we can use to identify ancient woodland on. The next sort of part of the project was identifying what model that we could use to predict these areas of ancient woodland. So the type of model that we used was something called instance segmentation, and you may have come across this in other contexts such as self-driving cars or for medical imagery. The image on the right here shows an example output of an instance segmentation model, where you can see the model has predicted different objects on the image and the location of these images as well. So this is really important for us because we don't just want the model to be able to predict if woodland exists in an image we pass into it. We want to know exactly where in that image woodland existed, because that's most useful to CADU to identify what area of Wales they want to target that contained ancient woodland in the past. So the outputs of our model is a bounding box. So this is like a rectangle or a polygon, a rough area where the model thinks an object exists. We've got the type of object that is detected. So in our case, we're interested in different types of woodland. We've got a confidence score between 0 and 1, which represents how confident the model is that that object exists in that area. And then finally, we've got a precise location. So these are a series of coordinate points, which allows us to accurately locate exactly where woodland exists in that area. So that's kind of like our high level overview of computer vision models. Going into a little bit more detail, the algorithm that we used was something called a masked regional convolutional neural network, which I will call masked RCNN from now on because it's a bit of a mouthful. So this is a type of deep learning model that learns features from a set of pre-labeled annotated images. So this is a series of training data that we've labeled ourselves, a very small sample, and the model will learn exactly what features are associated with areas of woodland that we've labeled. This allows the model to identify or to learn and recognise patterns that correspond with an area of woodland. So this might be the intensity, the distribution, or the patterns of pixels. The more data and the more varied data that we can provide to the model that we have labelled ourselves, the better the model will be at being able to predict on unseen data. So these are images across Wales that we don't use and we haven't labelled in training. And finally, important to note, the model will only be as good as the labelled data we give it. So if we are uncertain about where woodland exists, then that uncertainty will be reflected in the model predictions and the confidence scores that I mentioned in the previous slide. You can see the difference in the quality of data that we had on the right here as well. At the top, we've got a good quality map. It's quite clearly defined symbols. And if we were going to label this ourselves, it would be quite easy to identify kind of the boundary that we wanted to label, because the woodland is contained in a nice field. Whereas the image on the bottom is a poor quality map, which is just to do with the fact that this is very old data and has been scanned from kind of paper sources. We can see that the symbols are a bit more smudged. It's hard to distinguish between them, and it would be more difficult for ourselves and for the model to identify this area as an area of woodland, just because the symbols aren't as clear. So with this in mind, the next step was to create our training data. So as I mentioned, we took a very small sample of our nearly 600,000 images and labelled them, which was around 1,000. And a big shout out to the data science unit for spending some time in QGIS drawing polygons around areas of ancient woodland on these images. So these 1,000 images were sort of selected using stratified sampling. So this would ensure that the terrain that we were training the model on was varied. We didn't just want the model to see rural areas, for example. We wanted to learn the patterns of pixels in urban areas like terraced houses, which isn't woodland, but because the distribution of pixels, the intensity, how busy the image is, could be attributed as being similar. We wanted to make sure that the model had a variety of training data to learn from. And then we standardized the shapefiles that we created into coordinates between 0 and 1, which could be used in the computer vision model that we were training. So the types of labels that we used to decide whether an area of woodland was considered woodland or not was from the key or the legend that was available in the documentation of the landmark data. So our 6 kind of key symbols that we used to label included things like wood, mixed wood, fir, bushes. But as you can see, there were a lot of other symbols in the legend where it wasn't considered woodland, things like quarries, osiers, fissures, things like that. We can see the kind of variety of symbols in the 3 tiles at the bottom. We've got sparse wood, which are the tree symbols, but kind of distributed more widely across an area. We've got bushes, which again are a bit more easy to identify because we've got them kind of in a line, usually along a boundary. And then we've got mixed wood, which is a series of collections of quite varied symbols, which are being labelled as mixed wood. So these are some examples of our final labelled images here, and you can see that we've got kind of variety of different objects, some which is quite easy to label, some of which are more kind of spread out. Because this was kind of initial proof of concept, the first thing that we wanted to do is actually take all of these labels and assign a single label to them. So all of these areas would now just given the general label as woodland. I'll talk a bit later about the work we did to make like a multi-label classifier instead. But for now, and for any outputs that you see going forward, it was just attributed to the general label as woodland or not woodland rather than the specific tree type. So that was our data. And now we're looking at the first version of our model. And to do this, we needed to use the right infrastructure. So I talked a bit about the images having a lot of memory, and even by converting it to PNGs, it still requires quite a lot of computing power. So we couldn't use a local desktop to host or train any of these models. So we set up a project in the Azure Machine Learning Cloud Service, which allowed us access to storage, so we could store all of these 600,000 odd images cheaply. It had an environment where we could run our MassStar CNN algorithm quite simply, that we could kind of compare different runs and the metrics and things like that. And probably most importantly, it gave us access to compute instances like GPUs to speed up our training and predicting. The Azure Machine Learning Workspace, initially I was a bit kind of unsure of it almost, because you think a cloud service provider, it's different to a local desktop. So I wanted to give a bit of a background of what actually looks like in the interface. You can see on the right here, it's quite easy to navigate between the different components of this project. It's easy to look at the data storage. The notebooks was where we run our code, and they're essentially Jupyter notebooks. And we're able to version and control kind of who has access to this code via DevOps, which is like a Azure Git repository. And then most importantly, we've also got access to these jobs and experiments and endpoints. So this allowed us to scale up our training to predict on tiles across the whole of Wales, which was a major requirement for the customer, because although it would have been really useful to be able to identify and build a model with a small sample of data, really it was the whole of Wales that we were interested in when running our final predictions. So I just want to talk a little bit about what kind of the computer vision model actually does and a bit of mechanics behind the sort of backbone. So the master CNN is a type of convolutional neural network. So we use this to first extract features from our images, to scale and create some new features to allow the model to kind of distinguish between different images and to make it better to look at unseen data. It then proposes a region of interest where woodland could exist on a map, and then it predicts the label and exact location of woodland in that region. So the extraction feature part and the predict and label part relies on a weight matrices. So if we were going to train a model completely from scratch, that weight matrices would be kind of considered as random. But because we use master CNN, the starting weight matrices are actually from a publicly available model, which has already been trained on nearly 200,000 images from a Microsoft dataset. So it starts off with a good basis, if you like, to identify different objects in an image. We then run this sort of epoch or a stage where we update the model weights each time. We reward the model by whether it's predicted accurately or not. And we found that the best model performance was after training this master CNN on our data over 6 epochs. So this ensures that our model is specific for the type of data that we are interested in predicting, so this specific historic landmark data. But it also means that the training doesn't take as long as it would do if we were building the algorithm from scratch. So I talked a little bit about performance there. So how the performance is assessed. So we use a primary metric which combines 2 more traditional machine learning metrics, precision and recall. So precision is the percentage of correct positive predictions out of all our predictions, and recall is the percentage of correct positive predictions out of all of the labeled data. So this is visualized in the image below. The image on the left is a representation of actual labels. So we've got 10 tiles, 2 of them which have been labeled as woodland. And then the image on the right is after the model has predicted. And in this pretend example, the model has predicted an area of woodland on all 10 tiles. So the recall would be 100% because technically it has identified our 2 actual labels, our 2 actual tiles as being woodland. However, the precision would only be 20% because it's identified a lot of areas where there are no woodland as containing woodland. So it's a real balance between our recall and our precision to ensure the model identifies and predicts as much ancient woodland as it can, but also reducing the amount of background which is being incorrectly identified as woods. And this is the kind of performance, which is called average precision, which takes into account these 2 metrics. So it's the area under a curve of a precision recall graph. And our first average precision score was 0.46. So we'd already kind of tweaked and tuned the model and had seen some improvements in this score. So we used this first version to visualize the predictions to see exactly how good the model was at identifying areas of woodland when visualized on a map, as well as comparing our training label data and the predictions. And this is the next part where we actually kind of show some of the outputs of this first version. So the first thing we did is plotted the model's results as individual images. And you can see a variety of different tiles here and the model's predictions. So for each prediction, we've got a polygon. So that's represented by the kind of block area. We've got a bounding box, which is the rectangle or square around the boundary of that polygon. And then they've been coloured in by its confidence score, red to green, green equal to 1 equal to most confident. And you can see that generally the model is more confident at predicting our kind of areas of woodland which are contained in a boundary, and less confident in predicting these areas of bushes. And this is kind of what we expected based on how we labelled the data ourselves. It was much easier to label big, large areas of woodland contained in that boundary compared to trying to decide whether a line of trees was considered woodland or not. And although it was useful to see the like images sort of as individual tiles, the next thing we needed to focus on is how we could make this usable and scalable. So we did some processing of the predictions to basically combine them into polygons, which we could then open in a geospatial software. So these are the 3 images to represent this process. The one on the far left is no predictions at all, but you can see that there are areas we would expect the model to predict woodland in. In the middle is our rural model predictions. So you can see there are quite a lot of kind of individual objects here. It's good to see what the model is identifying as woodland and not, but it's less useful if we were going to open it in a shapefile, for example, to see exactly kind of what area we would be interested in. And so the final image on the right shows the process predictions where things have been dissolved into kind of single shapes. You can see that the green and the red, so this represents areas of woodland that we have removed because they don't match the Forestry Commission's official definition of woodland. So this means that we are only retaining the large areas of ancient woodland on the map, which matches that definition. So finally, once we processed the predictions, we could then save them as a shapefile. And we can see here the outputs of what it looks like when we join all of our predictions into kind of like a single image. So the red tiles represents our individual 200 metre by 200 metre squares, but joined together, it's much easier to kind of review and to see it over a large area that's plotted back onto our original map. So although there were lots of like positives from this first like kind of trial run, there were still some things that needed improving. We still had some gaps of white space in the predicted polygons. Some wrong symbols were being identified, particularly kind of like shoreline and coastal areas or cliffs. We can kind of see why that might be the case, because again, the distribution of pixels for a cliff might be similar to the distribution of pixels in a large area of woodland. And then finally, we had a problem where map text was being identified as woodland. Again, this was due to the fact that when we were labelling areas of woodland, the woodland name was often included in that area that was labelled. So the model then predicts a non-wooded area that also contains text as being woodland for this reason. So we made some updates and some additions to the model. So we added a new category for shoreline and another category for cliff-like structures. Basically, these were exclusion categories. So the images below here shows the first version of model, where we've got contour lines being incorrectly predicted as woodland, and the second version of the model, where instead the contour lines have been predicted as cliff-like structures. So these can be then removed from our predictions, and our second version of the model doesn't contain these sort of mispredictions. So we're more confident that the model outputs will actually represent areas of woodland rather than areas of an image which might look like woodland. With these changes, we made some updates to the model parameters and post-processing steps also, just to make the final output more usable as well. And then once we'd done this, we were ready to start reviewing the predictions. And these 2 images here show how we reviewed some of the process predictions on the left. So these are the model outputs. We can see that the model's predicted an area of osier and an area of mixed wood. And then the image on the right are some satellite imagery from the 1940s, I believe. So this is kind of like the earliest satellite images that we have to use to validate the model's predictions. And we can see the model's done like pretty well at identifying the areas of woodland here. And we can also see that although it's done well at identifying the osiers, these are not as covered when we actually look at the geography compared to an area of mixed wood. So with this validation, we were then ready to apply it to across Wales. So the number of images that we used for our predictions in the end was near 500,000. It took 40 minutes to train, and then around 3 hours in total for predictions. So we like cut down, I guess, the time that it would take to manually review these or manually label this data quite dramatically using this process. And then our kind of final slide of the current project was identifying these areas of lost woodland. So like going back to how we could actually use these in reality. So the image on the left shows our OS landmark map. It shows the areas of the map that has been predicted, so that's in green, and it shows the areas of in purple, which are areas from the ancient woodland inventory, which is another data set which includes areas of ancient woodland from this period. So we can see that the model prediction identifies other areas of ancient woodland that no longer exist currently, so we wouldn't expect them to be on the ancient woodland inventory. We can see, however, if we look at satellites, these areas in reality wouldn't be very good to focus on replantation efforts because it now contains an industrial estate and a road has been built and things like that. But if we look to the image on the right, we can see again the model has predicted an area of woodland based on the historic map, which we can see existed. That hasn't been identified in the ancient woodland inventory because it no longer exists in current geographies, which is validated at the satellite image at the bottom here as well. So this would be an area that would be useful for replantation purposes because we can see there's opportunity to plant trees there because trees no longer exist, but the space is there if you choose to do so. And that's kind of like our wrap up. So before kind of finishing off, I wanted to talk a little bit about how we should be using these outputs. So although the kind of the model outputs have been promising, we wanted to emphasize that these are experimental estimates and they come with caveats. So as you might have seen in some of the predictions, the model does not
consistently Are you heading off for lunch soon?
Predict the area or type of shape when identifying areas of woodland. So if we were going to use them to calculate the area coverage, for example, the shape or size of the polygon would return inaccurate results, particularly if we extrapolated it up to the whole of Wales. So instead, we recommend these predictions to be used to show where it is likely for what lost woodland to be located. And these outputs can be used as evidence to support policymakers' decision-making relating to woodland replantation, along with other sources like the ancient woodland inventory. So we can use other kind of metrics like the confidence score to support this rather than the exact location of the model prediction. And more recently, we've been looking at whether we can use this work to identify different types of trees as well. So our feedback from CADU and stakeholders has been positive, and we think that it is worthwhile to have a look at being able to identify the specific labels that I mentioned before, like mixed wood, fir, wood, and that sort of thing. And the early results have been promising as well. We might need to change our categories to group labels together, but the model's done well at being able to distinguish between different types of trees, particularly when the shape of the woodland is quite distinctive, like bush, mixed wood and fir. And what's our next steps? So the best version of our model is currently just predicting areas of woodland and background, so it's not going into distinguishing between different types of trees. And once we've quality assured this outputs internally, we'll be releasing a shapefile on Datamap Wales. So someone could download the files, open them in QGIS or ArcGIS and have a look and review the model outputs. And with that, we're very keen for feedback and improvements. We want to update it to use for our future multi-labeled versions. And so we're keen for kind of any responses on how you've been using the data, what's worked, what hasn't worked, so we can update future models accordingly. And that's the end of my slides. Thank you very much for attending. Does anyone have any questions? I've also got a link to the blog that we published last week as well, if you want to find out a little bit more, and happy to answer any questions now. If you want to send us an email, this is our email address here too.